Så, välkomna hörni tillbaka till Tech Arena, InDesign, Innodex-scenen. Jag står här med Christoph Mattei från Föreläsningen Dynamics. Switching to English now. Material choice for sound and vibration dämpning. Yes?
Yeah, of acoustic performance, we call that.
Yeah. That's an important step in the process for a thoughtful acoustic design. And you guys have a smart design process for this.
Yeah, well, I was thinking to discuss about the different way you can go forward when you are working with a product design where sound is going to be an important part of it. We are acousticians. We are working both with simulation and measurement, and it's a little bit an explanation of the tools and process you can use to choose the right materials so that your final product is sounding the way you want it to sound.
All right. So before we get really into the deep tech area of what you guys are doing, because you're in the same area as we are with the Innovative Materials Arena down there. What? Oh, you have a demo down there.
Yeah, so we are working, helping companies with acoustic in general, both doing measurement, doing simulation. We are also developing products around active noise control, which is another way to reduce sound, for example, in cars, where you are sending the anti-noise, for example, the same process as you have in a headset, but we are doing that in volumes like a car or a room. So we have a demo showing active techniques, and the talk today is more about passive techniques, using passive materials, but making the right choice for these materials. So these two techniques are complementary, I would say.
Right. And why do we need two different techniques?
There are techniques that are working a little bit in different ways. I will show a little bit typical performance of materials. Usually, passive materials are working well in high frequency or middle and high frequency. It's a little bit tougher, or you need a lot of materials to be able to, for example, attenuate sound at low frequency. Where active noise control, on the other hand, they are very efficient at low frequency. It's a little bit more challenging at high frequency, though. So you can say that it's two techniques working in a complementary fashion.
For low and high
for
frequencies.
For low and high frequency.
Right.
Yeah.
And just to give the audience a area of where we're at, like the market for you guys, is driver experience, kind of?
So the market that is clearly emerging for active noise control is indeed the automotive industry. Right. We are part of a tier 1 automotive industry, HVA Group, which is developing and offering almost all the product in the car. So today, the expectation of electrical vehicle and the comfort in electrical vehicle is that you are going to sit in a silent car. After 40, 50 kilometers an hour on a road, the level of the sound level in the car is absolutely the same as in an internal combustion engine car. And this mismatch with the expectation of the end user is pushing this type of active noise control technique a lot, and we see now a market for this technology, which are using the audio system of the car and relying on real-time software to produce this anti-noise. So that's also a part of our portfolio that is right now important.
All right.
But today we will not talk about that. We'll talk about material, because we are from the Innovative Material Arena and the connection between material and acoustics.
All right, let's deep dive into that.
Thank you.
Welcome.
So as Pia mentioned, if you want to know a little bit more about acoustic, we are just on this stand. And Föreläsningen Cryodynamics is a company that is working with offering expertise and supporting other companies within the field of acoustic and vibration, where we can do measurement, we can support with simulation, fluid dynamics, and environmental engineering. And here what we mean with that is the study of vibration, acoustic, and thermal environment. For example, for electronic, we work in tough environment, as you see here. And we are based in Linköping. But today, the topic is a little bit a general topic, I would say, about how to, as a designer, as a product designer, how to choose the material that you're going to put in your product in order to ensure that the material is going to have a good sound signature or response. So why is it important? Well, because we know that the way we interact with product that makes sounds, you can take a vacuum cleaner, or is going to change depending on how this product is going to sound. Either the behavior or the way you like the product is being influenced by the sound of the product. Usually you can talk about the 3 I when it comes to sound. You want to keep what is informative. You need to have this relationship with the functionality of your product, so you know that it's working. You often want to take away what is irritating, so loud or tones that you can feel like as irritating. And in some cases, for example, it's very important for engine design. You want to keep the impressive sound of your product. So these 3 I's are really the goal of an acoustic designer, or the way you are going to deal with acoustic in your product. And in most of the products that involve a sound source in the product, you are going to have to work with materials that are going to help you to get the final output. And here we are going to look at tools and process we can use, from measurement to simulation, to be able to end up with the right performances. So if we start a little bit about how sound is interacting in your product, what are the different ways you have to affect sound from a sound source? We can identify 2 main processes. The first one is called diffusion, and it's a process where the sound energy is being reflecting on a specific structure, and is going to be, the energy of the sound is going to be scattered in different regions. So it's typically the type of process you can use in, for example, building acoustics, where you are positioned where the sound is, and you want to use diffusion to even a little bit the level of the sound. And usually you can act with the geometry of the material. But the other process is absorption, which is using the fact that the sound is going to go through a material, and we lose energy when propagating through these materials. And this absorption is happening inside the material due to different processes that we will talk about. And this you can control by choosing material with different structures or different morphologies. And that's where the choice of material is very important. So we will put ourselves in a situation where you have a source which is inside your product, and you want to control how much of the sound from your source is coming out, which is a typical design case, and we will then consider more the case of absorption. So what are the phenomena, what are the materials I can use to optimize this absorption, and what are the phenomena, the physical phenomena that can be used to do that? There are 2 main processes. The first one is energy dissipation. So the structure of the materials, often we are talking about porous materials, is going to lead to a lot of loss in the material, so energy loss that can be due to friction or dissipation of the energy. And these materials are often, I don't know if this is working. Oh. Sorry, this one. Well, it doesn't seem to work. These materials are usually going to absorb the energy very well in high frequency. That was what we were discussing, and a little bit less in low frequency. Another process is to trap the energy in structures. So small, for example, cavity with a neck like that are so-called Helmholtz resonator, and this type of small cavity are playing like a mass spring system, and this mass spring system can absorb energy, and usually these materials, you can tune them to a certain frequency when you have frequencies that are coming up, where you can increase the absorption. And you can find, for example, in anechoic rooms, which are the rooms we are using as acousticians to do a measurement, the combination of these two phenomena, where you have these big wedges that are trapping the energy and absorption on the wall. So that's the phenomena we're working with. When we do design, often the typical situation is I can find a porous material, a foam, or some fibers, and I want to know which are the property and how do I relate the property of material to the final performance when my material is in my product. So the way to do that, I think I lost, yeah. What we are doing here and what we want to do is really to be able to couple the microstructure of the material, so how it looks like with pores or fibers, to the final property. So the first way to do that is to do measurement. And we have different ways to measure, but usually we put ourselves in very well-controlled situation. For example, with this type of device, which is a tube where you have a noise sources on the right, and then you put your sample that you have prepared on the left side. And the fact that we are in a tube is going to make sure that we have a very simple case of interaction between sound and material, a so-called plane wave, only one frequency. And this simple case allows us to give us a very clear and quantitative information about the properties, the acoustic properties of the material. Typically, from this configuration, you can get an absorption curve, which is often a function of frequency, where you know when you are an absorption of 1 give you a total absorption, and you see the behavior. This is a very, and this information is also usually the information you get when you buy a material and you want the specification, acoustic specification on the material, you will get a curve like that. What is very important to understand is that this specification is valid in this simple configuration. When you are going to take your material, put it in front around your source in your design, you very seldom can exactly use this quantitative data. And what you are as a designer is to predict what will be the sound of my product. And this information is not as it is usable. So the other approach we can use is based on material models, simulation tools. And there has been since the 1960s, a lot of work that are looking at coupling the structure of porous material with their acoustic performance, and a number of models. I will not go into the detail, but what these models are doing is that they are coupling physical information about the morphology, so porosity, density, flow resistance, these kind of things that are really related to the material, to the final property in terms of parameters that are usable for a simulation. So we are talking about acoustic impedance, about boundary conditions. The important thing is that these models make the translation between the physical parameters to something that can be used in a simulation tool and embedded in complex geometry. So here we have a link to being able to simulate in complex geometry. The difficulty with these theories is how to extract these morphology parameters, because they are not so easy through looking at the picture, it's difficult to be able to say something about porosity. And the difficulty here is to really get the information about the input data to these models. So I'm going to discuss a practical problem that we have worked with at Föreläsningen for more than 5 years ago, but it's a real case problem, and to show a little bit how we can combine these tools. We had an inquiry about a turbo compressor that was linked to an inlet tube. This turbo compressor was making a lot of noise through the output of the inlet tube. In this configuration, the air was going down to the turbo compressor, but the noise was going up, and there was a very high noise level, and we had the question, how do we do to reduce this noise by X dB? That was a very quantitative requirement, and the idea was to put absorbent material on the tube, and the question was, considering this noise source, what is the type of material, what is the thickness, what is the type of material we need to use to get this noise reduction on the outside. So the way we worked through this problem was to start with different material type. You always start from some hypothesis, but then we had to set the material parameters with precision to get the performances. So the way you can link these two approaches is to start with this measurement in a rig, which are in the control environment, and to get some parameters, acoustic parameters. Here, this is an impedance curve, which is for a description of the acoustic of these materials. And what we did was to use this model in this simple configuration to fit the measurement. So if you use this material model in a simple configuration, you will get a simplified representation of the material that you can set, then put in simulation tools, and do the link between the material morphology and the performance. And as a next step, you have all the information you need to do a simulation. So here we are talking about finite element simulation that are there are a number of tools on the market to perform these simulations. The point here is that we have a clear link between the material we want to test and we can and its properties, and we can put them in a full model with the actual source, which is the second point, the description of the source. And in that case, we had also to take into account the flow in the tube. This simulation gives you exactly what is happening in the tube in terms of acoustic level. And here, the important information is what is the absorption between this point and this point, the two positions of the treatment, and to be able to determine with the simulation at the design stage the performance of the situation. So you have the whole process that is established, and basically what is needed then is to iterate. In that case, we needed to iterate 2 times. Ended up with some performance that were fulfilling the requirement and being able, and then to go to the next step. The next step is building this system and testing it in a test lab or in the real situation. So what I want to show here is a little bit how both this control measurement of materials that are giving this, I would say, type of information you get when you look at material specification, and simulation that allow you really to describe the complexity of the situation you are with your product. Usually, if you take a vacuum cleaner, the acoustic phenomena happening inside the vacuum cleaner or around the fans are quite complex, so you need to take into account this complexity and to combine these two information to get a real, to get a process that gives you prediction about the performance of your product, allowing to iterate to find the right product. So in conclusion, material selection is something that every designer is working with, and it's also true when you want to focus on the acoustic performance. We are dealing with actually quite complex material. If we look at the interaction between acoustic and porous material, it's quite a complex phenomenon, but we can make use of these models and interface them with finite element simulation that allow us to do some virtual acoustic prototyping, which is something that at Föreläsningen Creo we are used to do and do in a different type of situation. So that's the conclusion of this insight on acoustic design. If you have any question or if you want to discuss a little bit more of this kind of process, we are sitting at the booth here, and I'm happy to discuss with you.
All right, thank you, Christoph. Very nice. Does anyone in the audience have a question now? Would you dare? No? Okay. Pierre, do you want to add anything? I'm looking at Föreläsningen's head CEO in Sweden, right? Yeah. Would you like to add anything?
Thank you. Now, just to come back to the first information that Christoph was sharing, that ANC, the active noise control that you have in your headphones today with noise cancellation, this is really coming to the market in automotive industry, and we have excellent software developed by Creo here in Linköping. That is really amazing. So, if you have any questions or information you would like to learn more about it, we are happy to answer these questions. Thank you very much.
Thank you, Pierre. So, if you want to try and have a demonstration of that active noise control that Pierre just mentioned, they have that in their booth down there. I have a question. Of course, it's going to be on a more high level because I'm not a technician like you guys are, a researcher. But what would you say, Christoph? Because I interpret your presentation as Creo being kind of unique in this design process way of working. Is that correct? Would you say that you are unique on the market?
I'm sure you can find people who could do a similar thing. What is a little bit specific at Creo is that we've been working both. We have the two aspects of being able to work with simulation and experimental case, and being involved in a lot of design problem. So making these connections is something that we are doing every day. But what is important is to find to understand that you can get a lot of information from the material, and then to be able to understand what are the steps that needs to be done to put that to your problem and to get to quantitative estimation. What you want to do is to be able to predict before you start building how much the product done. So this is I would say we are used to deal with this type of problem.
All right.
I'm not going to say we are unique.
You're not going to brag. Okay, well, that's fine. What would you say would be the biggest challenges that you meet now with this in this market?
Well, in terms of the issue of being able to reduce noise from product is something that is I would say will be there and needs to be there. I think the challenge is to explain when you have people coming with you with a question about a product, to be able to very clearly explain the different steps that are needed, and to be able to have an understanding on the best way to go forward. There's always complex issues. There are complex physics behind, and you have to explain that. And we are working for different type of application, from automotive to aerospace, where this is something that is taken very seriously in this type of product design. So yeah.
Right. And how would you apply sustainability to your work?
So I guess all this type of, maybe I don't know if the motivation is sustainability, but it's a consequence of it. The motivation is often to get robust design before you start building something. Usually cost is the driver, because it costs a lot to develop prototypes. But indeed, you end up with a sustainable process, because before starting, you know exactly where you are going. You have simulation, validation, and I would say virtual prototyping, virtual design is, in a sense, sustainable, because your first try will work. That's the goal of it.
Right. So you don't have to try with the real materials until you actually know what you're doing.
Yes.
Right. Okay. So if you want to talk more to Christophe or Pierre, they're down there. Thanks for listening. Thank you again, Christophe.
Thank you.